Okay, hello everyone. I hope you're doing fine. So this is me just trying to come up with some content on RabbitMQ, and I shared a video yesterday, and there was quite some nice engagements from it, and I saw the need to come up with another recording that kind of explores these concepts from the very beginning. Of course, I know we said I'll be sharing kind of like from where I'm at currently. I just saw the need to start from scratch for anyone who's starting out. So I'll just reduce the audio for this. Yeah, I hope it won't be a nuisance. Yeah, but nonetheless, so let me just share my screen so that you guys can see it. This is live coding. Yeah, that's pretty much it. And then off we go. So we started with the introduction, at least, to RabbitMQ, and this video is gonna be an overview of what RabbitMQ is all about, and then we won't code live. What I'll do is I'll just share the learning materials that I already have, of course, a bunch of markdown, and then you can later on go and write the code yourself, as I have done. And so yeah, so we're gonna start with what a messaging queue is. So a messaging queue from this documentation is just a component of inter-process communication. So you have you want to decouple various services in your application. You're building a microservice that has say for example a user or authentication service, and then there's an emailing service, there's an analytics service. So you have various services decoupled and you want them to communicate. So instead of them communicating via HTTP calls, you can just have one publish a message, and then the other receives the messages, and then it does whatever it wants with that specific message. So that's in a nutshell what messaging queues do. So they just pass control or data or messages, for this case, between separate processes or services. So the common analogy that is given even in the RabbitMQ documentation is, you think of it like a post box, and then the sender drops in a letter, and then the receiver picks it up later. So it doesn't matter when either when the receiver is just there, when the person, the one who's bringing the message is there, so they can always take it later, and then neither have to be present at the same time. That's ideally what I'm trying to say. And then once the letter is picked, it's deleted from that storage where the mailbox. So RabbitMQ is a message broker, essentially the digital post office, and then it just sits in between your services. So this is what the queues are doing for us. They're responsible for receiving the route. So RabbitMQ is very good when you have like complex routing, and then they deliver the messages reliably. Of course, there's a lot of things that come into action when it comes to delivering these messages. And yeah, so we have the hello world, which we won't look at. The trait that you must always understand with RabbitMQ is the concept of being a smart broker. So if you ask any AI model to explain to you what RabbitMQ is all about, it mentions this when you're trying to kind of get the difference between RabbitMQ and Kafka. One is a smart broker, the other one is a smart consumer. So for RabbitMQ is a smart broker, and then we have dumb consumers. So RabbitMQ handles all the routing logic, so consumers just pull from the queue without needing to know who sent them and why. That's pretty much it. So the consumers are just linked to a specific queue. They consume messages from a specific queue, but the one who's handling the routing and all those things is by the broker, is the one that is doing all these things for you. So what are the key concepts that one needs to understand when it comes to RabbitMQ? One is a producer. So producer is the one who's publishing the message, and then an exchange. So this is the person who's receiving the messages from the producer, and then it is responsible for routing them to queues based on specific rules. So a sign up event can go to an analytics service, it could go to an emailing service, it could go to whatever service if you're performing auditing and whatnot. And then an exchange. So this is the one that receives the messages from the producer, and then it routes them to specific queues based on the rules. So we have one publishing the message, and then we have an exchange which is sitting in between that is responsible for routing the messages, and then we have a queue. Now this is just like that mailbox. So stores messages until a consumer picks them up. And then the consumer, this is the one who's subscribing to a queue. They process the message, and then they send an ACK. So ACK is just like short for acknowledgement. So the consumer needs to acknowledge that, okay, I've gotten this message, and then it's deleted from the queue. Binding is a key concept because it's the one that links a specific queue to an exchange. So we have an exchange that acts as an intermediary between the producer and the queues. So an exchange gets the message and then it routes them based to various queues based on the binding that we have there. And then we have the routing key. The routing key is now the one that is responsible for the routing. So a message attribute used to exchange and then decides which queues the exchange sends the message to. And that's pretty much it. So we come from the producer, goes to the exchange, and then exchange, you can have a bunch of queues. And then how the message comes from the exchange to the queue is because we bind them together. You can bind them with or without a key, and we'll get to see that. So after the consumer processes a message and sends an acknowledgement, or what we call an ACK, RabbitMQ permanently deletes it from the queue. Again, sorry, I'm not on light mode. I just prefer this. And then the exchange types. So the exchange types are very, very, very paramount for you to understand. And then they are the brain of RabbitMQ. So there are 4 types. We have direct exchange. So this routes the message to the queues whose binding key exactly matches the routing key. So this is like a specific. So we have a specific binding key that matches to an exchange. So an example is we can have an order service. We have it publish with a specific routing key like order.paid. So whenever orders are paid, we have a queue that processes that. So for example, a payment queue, and then it hits a payment service. So a producer would be an event that triggers a payment or an order created, for example. So it needs a payment for it. So it goes to a payment queue, and then the payment service processes the payment. If it's cancelled, so we have an order.cancel. So this is another queue. So it has a different key. So we have order.cancel. So cancelled could be the key for that, and then the refund queue is triggered. Fanout Exchange. So this one ignores the routing key entirely and broadcasts to every queue bound to it. A perfect example is when a user signs up. So a user signs up, this is the producer, you publish the message, goes to the exchange. So for this case, it's a fanout. And then this is very important. Fanout is quite good when you have a scenario where you have various services depending on a specific event to be created, like a user sign up. A user sign up would need a profile service to create the profile. It would need an analytics service if you're performing auditing, or you just need like analytics to be done. And then you also have the email service. We need to send an email to the user, or even a notification service. So that's a fanout. So every queue gets a copy of that specific published event. So this is what we're talking about. We have an email queue, a profile queue, and an analytics queue. So everyone gets a copy of that specific message. That's a fanout exchange. A topic exchange, on the other hand, is we route based on pattern matching. So this is kind of interesting, what I'm currently exploring. And it routes based on pattern matching on the routing key using wildcards. So there are scenarios where you want all the messages to go on a specific queue, and then they might be having kind of the same pattern, but you want a few of them to go to a specific queue. So we have star. So star matches exactly one word. So you might have something like logs.error.payment. So this would match bindings like, say, logs.hash. It means that it takes everything else after the log. So this hash would take the error and payment. So that would work for this case. But if you say log.star, so it needs these 2 words need to be very identical, and then here we can take any word. So matches exactly one word, and then matches 0 to more words. So the routing key, this is the example I've given. So you have a producer, and then we log the errors for the payment. Logs.error.payment comes to the exchange, and then logs.hash, it would take everything. It would take from this producer, and it would take from this producer, because we're just starting from logs, and then everything else can fit in there. So it will take these 2. And then logs.error, it means it takes from this. So if it is logs.error.payment, logs.error.signup, they'll come to this queue. And that's pretty much about the topic. So those wildcards, very, very interesting. And I guess this is one of the most common used. And then we also have the headers exchange. So headers exchange is we route based on the messages header attribute. To be honest, I haven't tried this instead of using the routing key. So useful when routing logic is complex and can't fit a simple key pattern. Example is when you route messages with header format like a PDF to one queue and then CSV to another. So you might have a format PDF processing would go to a PDF processing queue, and then CSV processing would go to a CSV processing queue, and then various services could consume them. And that's pretty much all the logs you need to understand. You need to understand direct exchange, fanout, topic, and headers. A lot of emphasis on the three, and then if need be, because I've not encountered this, we possibly could explore some other point. And then the other concept you need to understand is now message acknowledgement. So when a consumer receives a message, RabbitMQ waits for an acknowledgement before deleting it. You can have manual acknowledgement, or you can just have automatic acknowledgement, such that if an exception doesn't occur and the consumer gets the message or that, it automatically acts it. But on the contrary, you can have manual hacking. So there is two ways to, but manual hacking depends on what you're doing. If you're having worker consumers or worker queues, sorry, you'll need to perform some manual hacking, but we'll look into that. Yeah, so this guarantees delivery, and then if the consumer crashes before hacking, RabbitMQ requeues the message. So this is a very interesting point, because where the concept of requeuing a message, we are either looking at how do we perform the requeue. So if a message fails, do we send it to a dead letter exchange, or how is the logic like for requeuing? Because if a message keeps on failing over and over again, we'd get what we call poisoning. And poisoning is when it's a loop, an infinite loop of trying to requeue that message and relaying it to the consumer. So, but the idea is RabbitMQ, you publish a message, the consumer gets, so for this diagram we just eliminated the exchange and the queues. So the message gets to the user, the message is processed, the user or the consumer acknowledges it, and then the message is deleted from the queue, and that's it. So if the consumer crashes before acknowledgement, message is requeued. So this is another concept that we can look at later. The other interesting concept I came across when learning about RabbitMQ is the RPC pattern. So remote procedural call. So sometimes a service needs to send a request and wait for a response. In all honesty, I haven't tried this as well, but I just know about it. So when you need to wait a response, so you'll still want RabbitMQ instead of HTTP call. So but it depends, yeah. So the RPC, this is just like the remote procedural call, and then so this is how the hierarchy looks like. So we have a client, they publish a request to a queue, and then with a reply to or a temporary callback queue and a correlation ID. So this is what you publish a message, and then this is the request, and then you have a reply to, and then this is the queue that needs the reply, and then you have a correlation ID. So what correlates between the producer and the queue. So after that, the server consumes the request and then processes it and then publishes the response to that. So it goes like that, and then we have the server, it consumes the request, processes it, and then the server publishes. So it responds, correlation ID, and that. After that, so the client listens on its callback queue and matches the response using the correlation ID. I haven't in-depth look at this because I haven't seen the need for it, but this is just when you need I'm trying to think of a scenario where we'd need to do this, but the example when you need synchronous style result but want reliability and decoupling of a message broker, e.g. We have a pricing service that must return a calculated price before the checkout can proceed. So that's when kind of you need to perform this. That's about the whole thing of RPC, but I wouldn't worry a lot about it for now because yeah. So the very best way to learn something is to know where to use it and various scenarios where this kind of architecture is used. So we have asynchronous microservice communication. So a scenario is a customer places an order, and then instead of the order service calling the payment service directly, so this is what we call tight coupling, or just blocking. So it means that when the customer places an order, nothing else can go on because we are waiting for the payment service to respond. So it publishes an order placed event, and then the payment service consumes it when it's ready. That's ideally it. the whole asynchronous microservice communication. So this is how it looks like. So an order service, you place an order in an e-commerce application. So of course it's a microservice architecture. So you publish the event called order placed, and then it is taken to the exchange. So remember what we talked about, this thing. The exchange now routes the message. So for this case, it could be a Fanout, because everything else is getting, the notification queue is getting it, and also the payment queue is getting access to that order placed event. So this payment service processes the payment, and the notification queue emails them or sends them an SMS about their order. So it depends with how you kind of structure your application. So the order service doesn't really care if the payment service is low, temporarily down, and then messages queue up and get processed when it recovers. So and that's pretty much that. So if, for example, this order placed was done, and then the consumers or the payment service or the email service are not available, so this message would be taken to the queue. So the queue would have the messages, and then once the payment service is up again, it would come and retrieve the message, and then it processes it, and then things proceed. So that's the aspect of decoupling. So one service is not like tightly coupled to the other. Background processing jobs. User requests a PDF export of a large report, and then here, for example, you're generating a PDF. This might take 10 to 30 seconds, and we don't want our user to wait for a long time. And then the other issue is, if you're doing this synchronously, the user would have to wait there for it to load for approximately, say, 10 to 30 seconds, and this would either cause a timeout or something of the sort. So alternatively, we can have our API endpoint like generate report, return a 200 a 202 accepted immediately, and then we publish a generate PDF job to a specific queue. So, and then a background worker picks it up and then generates the PDF and notifies the user when done. So that's kind of it. So we create an event for processing a PDF. We have a queue that is there for processing the PDF, and then the service for it processes it, and then once it's done, the user gets notified, and they can review that. The other examples that I've seen quite nice is sending bulk emails. So you're sending bulk emails, you can have worker queues that do that for you. So worker queues ideally are just like quote unquote kind of microservices, but micro queues. So you have various queues that could help you do the distribution. You're sending 500, and then you have like 10 worker queues, so they are processing the same message. All of them, depending on the architecture you use, they can get equal number of messages, or you can distribute the tasks for the emails depending on the architecture you use. So you can wait for, if one is free, give it something to work on, send the emails and whatnot. The other one is resizing. Yeah, ideally any intensive workload that needs the user not to wait for it, so they can be notified when it's done, you can definitely do that. Rate limiting, so you have a third-party SMS API, and then allows kind of 100 messages per minute. So you have a third-party SMS API, and then it only allows 100 messages per minute. So what you do is you publish all the SMS tasks to a queue, and then you configure a single consumer that processes all of them at a controlled rate, and then RabbitMQ buffers the excesses without dropping the messages. So you just, these SMSs, they are there in the queue. So if your service just processes 100, you buffer all of the messages there, and then your queue would be consuming and processing all the 100 messages per minute, and that's so you don't like lose them. Event-driven Fanout. So a new product is added to an e-commerce platform. So on like a product created event fans out, we fan out searching index, inventory setup, CDN cache invalidation, analytics pipeline. All these are independent services that react to the same event with no direct dependency on the other. So this is just like the example you gave above when a user signs up. Other key concepts that you need to understand is 1, durability and message persistence. So by default, queues and messages are lost if RabbitMQ restarts. So you need to set that the queue is durable, and then to survive the crash or reboot, to survive the few things that we've mentioned, one is durable queue. So the queue definition survives a broker restart. So if your broker restarts and it had published messages, if you don't set it to durable true, it disappears. The messages, once you restart your broker, once you restart it, or the publisher, it disappears, that message. Persistent message. So this is the message body is written to disk, not just held in memory. So all of this must be set. I'll show you possibly in the next video. You can set them in the UI, you can set them in the application, and then that's basically it. So both of them must be set, and then a persistent message is an undurable queue, is lost on restart, and vice versa. So that's pretty much it. Yeah, example gotcha is you set up a durable queue in dev and everything works, and then you deploy to production without marking the messages as persistent. So RabbitMQ restarts during an upgrade and all in-flight messages vanish. So you need to persist the messages to the disk. Yeah. So in Spring MQP, so advanced messaging queue protocol, the queues are durable by default, and messages can be made persistent by setting the message delivery mode to persistent. I have to actually look at this, but yeah, this is very possible, and Spring is kind of making life easy for us. And then once you get to this level, we have what we call the dead letter exchange, what we call the DLX. So this is just ideally what happens when a message can't be processed. So by default, it is dropped silently, or you can figure out how to ensure that this message that hasn't been processed is handled right. A dead letter exchange gives you a safety net for this, and then all the failed messages are rerouted to a separate exchange or a queue instead of disappearing. So we have messages that fail to process. So a message gets dead lettered when a consumer rejects it with a requeue false. So requeue means okay, if you set requeue to true and you don't have a dead letter exchange, the message is gonna get back to the queue, and then it goes back to the consumer. It fails. If it's failing for the very same reason and you've set requeue to true, you'd have an infinite loop. There's that, and then the message TTL expires, and then the queue reaches the maximum length of the message and the message is dropped. That's pretty much it. So we have a producer exchange, and then we have a queue, and then the consumer rejects it. So no acknowledgement, or NAC. So it's rejected. So what happens is, if the requeue is false or the TTL is expired, we take it to a dead letter exchange, and then the dead letter queue, and then we have a developer or alerting. So you either get alerting or you have a retry logic that has been set there. So this alerting is quite important for a developer to go and kind of look into that matter and see why the specific message is failing. So why this matters is because without a DLX, a poison message, so this is what I was talking about, one that always causes the consumer to crash, can loop forever or silently vanish. So you can imagine you have Amazon MQ, that's what it's called, and then you have this message that is keeps on like repeating. Probably it's to the queue, to the consumer, and like that. So there's a lot of processing, and if you have a couple of messages like this, it means that your bill would skyrocket to an extent. So DLX is just like a separate queue where you can inspect it, alert on it, and then you can retry it after a delay. So the common use cases is you implement a retry mechanism, and then the dead lettered messages go to a wait queue with a TTL, specific TTL of course, and then they get republished to the original queue after a delay. Prefetch count, very important. This is very important. So you can run multiple consumers on the same queue, and then to scale throughput. So Rabbit distributes messages across them. So you have 1,000 messages, and then you want like the processing of this 100 messages. Like the same thing with the 100. You're supposed to send 500 emails. So if one queue or one consumer is doing that, so it's gonna be a bit challenging for that. So you can create workers. So, and then what happens is the messages are distributed. So you can have this specific worker work on like 50 messages, the other work on 100 messages, like that. So the problem with default round robin, so okay, there's round robin. Round robin is I give every worker gets equal share of work. So by default, RabbitMQ pre-dispatches the messages evenly. So consumer 1 gets 147 in that order, consumer 2 gets 258, etc. So if consumer 2 is slow, its messages pile up while consumer 1 sits idle. So we can get 50 all of us, but one of the consumer is slow. So one is gonna be left idle while the other one is still having a lot of tasks to handle. So how we do that is we have a prefetch count. So we set the prefetch count to 1, and then this tells RabbitMQ that don't send a consumer a new message until it has acknowledged the previous one. So we are trying to ensure that whoever is the same with whoever does more tickets is the one who gets more work, but the slow ones, they get less work, which is not like a very good thing, of course, when you're working, but that's the whole idea. So fast consumers naturally pick up more work, and then this is the key to fair dispatch and efficient horizontal scaling. So you want to ensure that as much as you want to process a lot of messages, so this other one is when you set it to 10, the prefetch count, you set it to 10. That means that, okay, everyone would get like fair. So factory.set default requeue rejected false, and simple rabbit listener container factory. This is where you set the prefetch count. But we'll get to see all of this. And yeah, publisher confirms. So Axe protect the consumer side, but what about the producer side? So how does a producer know RabbitMQ actually received and stored the message? So the publisher confirms, also called like publisher acknowledgements. They solve this. So RabbitMQ sends a confirm back to the producer once the message is safely returned to the queue and to disk if persistent. So that's the whole thing. If it's persisted, we let the producer know. But again, this I haven't like looked into in depth because I haven't gotten there yet. So without the publisher confirming, so a producer fires and forgets. So that's the whole idea with these queues. It's just a fire and forget thing for pub sub, yeah. So if RabbitMQ is overloaded or the connection drops mid-publish, the message is silently lost. So 3 confirm modes. We have simple, confirm after each publish. This is low, and the safest. Batch is confirm a batch of messages at once, and then async is RabbitMQ calls back asynchronously. So this is fast and it's a bit complex. So I'll have to look at this and then I'll share with you once I figure it out. But yeah, guys, so that's the whole idea with RabbitMQ. How many minutes? 27 minutes, 28 minutes. But in summary, producer, exchange, have a bunch of routing rules, could get very complex, goes to the queues go to the consumer acknowledges the message, and then the message is deleted from the queue. And then RabbitMQ shines when you need to decouple. Services don't need to call each other directly. You want resilience, you want messages to survive consumer, even when the consumers are down. And then scalability, you add more consumers to a queue to handle load. And then flexibility, route the same message with multiple services with different roles. And yeah, that's pretty much a summary of RabbitMQ, what it does and what it has for you. And yeah, so thank you so much for watching up to this very end. I hope you learned something from it. And next up is we'll look at a simple hello world in RabbitMQ and how to play around with it. And yeah, I hope you gain something out of this whole RabbitMQ thing. So thank you very much for watching up to this very end. I wish you guys a lovely day. I had to show you that slide, and see you on the next one. Adios.